Dear students, today we are going to discuss about the principle of equivalence from the Unit 1, non-inertial systems and fictitious forces. The principle of equivalence or the equivalence principle is generally regarded as a fundamental law of physics. Let us imagine that you are in an elevator. Have you ever thought of what happens when elevator begins to go up, or what happens when the elevator begins to down, or what happens when the elevator moves at a constant speed? And what happens when the wire hanging the elevator is cut? Or let us imagine that you are an astronaut on board on a space station. Have you thought about weightless? You feel weightless, or what do you do to make gravity in the flight? All the answers will be getting from the equivalence principle. So in the last session, we had studied about a fictitious force, or F is equal to minus ma. This is due to the force due to the fictitious force, and this is indistinguishable. The fictitious force is indistinguishable from the force due to a uniform gravitational field. Suppose a uniform gravitational field of minus a is there, so we will be not able to distinguish between these two forces. One is gravitational force, another one is fictitious force. Both are constant forces and it is proportional to mass. So in a local gravitational field G, a free particle of mass m experiences a force F is equal to ma, and there is consider the same particle in a non-inertial system uniformly accelerating with a is equal to minus g. Suppose this is in a non-inertial system that is accelerated at a rate s equal to minus g with no gravitational field. Here no gravitational field is there. So in this case the apparent force F fictitious is equal to, we can write F fictitious is equal to minus ma, or it is equal to mg. So there is no, suppose, see here you cannot distinguish between what is the case, what is the physically, what is these situations. F fictitious is equal to minus ma and it is equal to mg. In that case you are indistinguishable. These two forces are indistinguishable. This question was first pointed out by Einstein. So he illustrated a problem regarding this following a thought experiment that is called thought experiment. And in this Gedanken thought experiment, he arrived at a conclusion that conclusion of principle of equivalence, that is considered as the keystone of general relativity. So we can consider two situations we told in the introduction. One case when the a man holding an apple. So a man holding an apple in an elevator at rest. This case A is a man holding an apple in his hand and the elevator is at rest, and there is a gravitational field G downwards. He puts down the apple and it falls with an acceleration is equal to g. And consider the second case, this one is a same man, the same man in the same elevator, but the elevator being in free space, it is accelerating upwards at a rate s equal to g. So again this man puts down the apple and it again appears to him accelerate down at a rate g. So in these two cases are different. In one case this elevator is at rest, there is a gravity g. Here the this is having an upward acceleration as equal to g, it is going up, and he seems like he cannot distinguish between the acceleration of the elevator and the gravitational field. Here gravitational field g is there, here's acceleration of s equal to g is there. In both cases he feels like the same, he cannot distinguish between the two situations. So this is the thought experiment, Gedanken thought experiment Einstein had in his mind, and concluded in this. He had a conclusion of this. It states that this principle of equivalence states that there is no way to distinguish locally between a uniform gravitational acceleration g and an acceleration of the coordinate system s equal to minus g. That is, gravitational field is equal to acceleration. Both cannot be distinguished between these two, or acceleration is equal to gravity. This we have already discussed these points. Minus ms equal to minus mg, that we have seen that a is equal to g. So mass could be what is then mass? Here mass cancels each other, because these are found to be equal. Thus this mass could be measured by its acceleration, as in inertial force, given in the inertial force, or mass could be measured by its weight, as seen in the gravitational force. These two key situations we have to take in account. So this principle of equivalence emerges from the equivalence of inertial mass and gravitational mass, or we can say my is equal to mg. This situation is called weak equivalence principle, or WEP. From the WEP, the principle of equivalence emerges, because the equivalence of inertial mass and gravitational mass is considered. Ma is equal to mg. Then only we can get S equal to g here. Ma is equal to mg means here S equal to g. That is called weak equivalence principle. From this we have reached to a conclusion of equivalence principle, and there is no way to distinguish locally between a uniform gravitational acceleration g and an acceleration of the coordinate system s equal to minus t. This term locally has some meaning or significance that we will discuss in the next slide. So in the next, we are going to discuss the inertial mass and gravitational mass. There are two distinctive definitions of mass. One is inertial mass. It is defined as minus inertial force is equal to m inertial into a. Gravitational mass, or m gravity, can be defined as minus gravitational force is equal to m gravity into g. That is when Newton's equations becomes minus m inertial a is equal to m is equal to mg. So this there are two masses by distinctive definitions. So let us drop the two balls with the different weights, that is different m gravity. The same they are different m gravity means they are having both will reach the ground when we are ignoring the friction. Both balls will reach the ground at the same time. So m inertial is equal to m gravity. So this should be satisfied. Otherwise, the acceleration would be different for two balls. But in the previous experiments, we found that both balls will reach the ground at the same time. We know these experiments already, and in another uh, thought, Einstein had some other Gadankan uh, thought experiment, that is when the elevator freely falling in the gravitational field, what happens? When the elevator freely falling, the elevator and all its contents accelerate downwards at a rate g, and this man in the elevator, if he releases the apple, it will float as if the elevator were motionless in free space. So Einstein pointed out that this downward acceleration of the elevator exactly cancels the local gravitational field. So this from the point of view of an observer in the elevator, there is no way to determine whether the elevator is in free space or whether it is falling in gravitational field. So we have totally four cases we analyzed so far. One is the elevator coming down, elevator at rest, it is having gravity g upon it, and acceleration a is equal to g when it goes up. This is one case. Here the person inside this elevator has no idea what is happening, because whether he is in uniform gravitational acceleration or he is in an acceleration, uniform acceleration, or whether he is in gravitational force. So gravitational field as well as is equal to acceleration for this observer inside this elevator. The other two cases are when this elevator freely falling in the gravitational field. So this elevator and all its contents will be having an accelerated downwards at a rate g, and if he releases the apple, it will float as it is motionless in the free space. So this downward acceleration of the elevator exactly cancels the local gravitational field. So in that case, when in that case also, he has no idea what is happening, whether he is in a free space or whether it is falling in a gravitational field. So this apparent simple idea known as the principle of equivalence. This underlies the Einstein's general theory of relativity, and all other theories of gravitation. This principle of equivalence is as follows. There is no way to distinguish locally between the uniform gravitational acceleration g and the acceleration of the coordinate system, that is s equal to g, as I pointed out here. S equal to minus g, and acceleration is equal to gravity. Inertial mass is equal to gravitational mass we have. So an accelerated frame that can bring the effect of gravitational force, as we seen in the first example. First example was there is a gravitational force field G is equal to A downwards in the elevator A, and it is in rest, so it is in the field. The second one is no gravitational field, but the elevator is accelerating up at a rate A. For it is not, there is no gravitational field, and this acceleration A brings a gravitational effect. So an elevator moving in outer space, moving upwards with an acceleration S equal to G, can bring in a gravitational effect. And as I told earlier, there is no way to distinguish locally. The term locally means there is no way to distinguish from within a sufficiently confined system. This our elevator is a sufficiently confined. It's a small system, and there is no way to distinguish between these two situations. But this equivalence principle applies only to this such local systems. That is, for small systems, inertial and gravitational forces are indistinguishable. For non-local systems, they are distinguishable. So there are two examples in we have to study. First example one is driving force of the tides. Here it is distinguishable. That change is distinguishable because the earth is in free fall towards the sun, and according to the principle of equivalence, it should be impossible to observe the sun's gravitational force in an earth-bound system. But the equivalence principle applies only to these local systems. So the earth is but this earth is so large that appreciably non-local effects like tides can observe. So the tides are due to the variations of the apparent gravitational field of the sun and the moon at different points on Earth's surface. So this example we are going to look thoroughly. So there is a gravitational field of the sun at the center of the Earth, that is given by G0 is equal to GMS in n cap by Rs square, where Ms is the sun's mass. This is the sun, and the mass of the sun is Ms, and Rs is the distance between the center of the sun and the center of the earth, and n cap is the unit vector from the earth towards the sun. So the earth accelerates towards the earth is accelerating towards the sun at a rate s equal to g0. This g0, the gravitational field, or the sun, earth is moving towards the sun accelerated towards the sun at a rate s equal to g0. This suppose gr is the gravitational field of the sun at some point r on the earth, where the origin of the r is the center of the earth, then the force on mass m at r is given by F is equal to m into g of r. So the apparent force for the earthbound observer is F dash is equal to F minus ma. So with this we have already seen in the last class, F is minus F fictitious is equal to ma. From that equation, F dash is equal to F minus ma, or we can write m into it is equal to m into g ma means gr minus g0. The apparent field g dash r is equal to f dash by this m goes this side, thus f dash by m is equal to, it remains g of r is minus g0. So this is the the apparent field due to this sun on earth, and this is somewhat drawing that for the true field gr. This is the drawing to show the true field gr at different points on earth's surface. The variations are exaggerated here compared to this image. This is we are comparing all the places with the same field, but here we are considering the various places with different uh, field. The apparent field intensity is different at different places and different points on the earth surfaces. So GA, you can see this GA is larger than G0. This G0 is smaller than GA, or this GA is larger because it is point A is closer to the sun than the center of earth. This point A is closer to sun than this point, so it is considered as GA is larger. Similarly, GC is less than G0. The magnitude of GB and GC are approximately the same as the magnitude of G0, but their directions are slightly different. So the apparent field G dash is equal to G minus G0. That G minus G0 is the apparent. We already found that the apparent field G dash is equal to G minus G0. So this we have another diagram to show the different fields at different places. This drawing shows that the places A, B, C, D are having different G or the field. This G, A and G, C are, we are going to find out the first two cases, G, A and G, C. These two points we are taking into account, and in the next case we will be finding out the G, GB and GD. So this all points will be having different field intensities of due to this gravitational field. Gravitational field is different at different places. That is, we are going to show in this example, and the value we are going to calculate. So to find the value of GA and GC dash, that is our first point. So the distance from A to the center of the sun is RS. So this distance from A to the center of the sun is this is RS. Radius is this value is taken as RS, and RE is the Earth's radius. The Earth radius is RE. So we can write GA is equal to GMS. The magnitude of sun's field at A is GA is equal to GMS by RS minus RE whole square. And GA is parallel to GO. Here is the center is GO. The magnitude of the apparent field at A is GA dash is equal to GA minus G0. We have already found this. So GA is putting this value into GA, GMS by RS minus RE whole square minus G0. G0, the value of G0 is GM by RS square. This first equation we are putting in here. So we'll be getting GMS by RS minus RE square minus GMS by RS square. Taking this term outside, we will. So since this ratio RE bar RS, the radius of Earth to the radius, the distance from point A to the distance from A to the center of Sun, the ratio is will be less than 1. So we can use this binomial approximation according to this 1 minus x all raised to minus 2 can be approximated into 1 plus 2x. So while we expanding this our equation, GA dash can be written as G0 into 1 minus 1 plus, so we can write this as 1 plus the 2 into x. Our x value is RE by RS, and the etc. other higher terms minus 1. So from this we can cancel this 1, and neglecting the higher order terms, the final value will be 2G0 RE by RS. So that is what we are getting here, 2G0 RE by RS. We have neglected the other terms, higher terms like RE by RS whole square, and higher terms we have neglected. So we found the G dash and G dash C. GA is GA dash we have found here. So like that we can find the G dash C also. Then we will get the G dash if we find this G dash C. Now we have found G dash A, and if we are finding this G dash C, we'll be getting a different term. Like here all things are same, but the distance to the Sun is taken as, we have to take the instead of RS plus RE has to be replaced by RS minus RE. So therefore we will obtain a equation G dash C is equal to minus 2G0 RE by RS. This will be obtained for the we will be getting this equation for G dash C. So this equation is same like this, but the negative sign is there. So we can say that GA dash and G dash C are equal but opposite in sign. So this radially out from the earth. This is radially out. Like that we will find the G dash P and G dash D. This will be radially inwards towards the earth. That is the next slide. That is the apparent field at point B and point D. This will be finding out using the equation angle. We can assume angle is equal to arc by radius. We can assume that the distance between the Sun and the point B is approximately equal to the distance between the Sun and the center of Earth. We are approximating the approximately equal to the distance between the Sun and the center of Earth to the Sun and the point B. So we can write angle, we will get a triangle like this. So angle is equal to arc by radius, or alpha, it can be written as RE by RS. So this GB is not parallel to G0, but the we approximating alpha is approximated to RE by RS. So due to this approximation, GB dash, we can write GB dash is equal to I will write here. So this GB dash can be written as GB dash is equal to G0 into alpha. Alpha we have found it as RE by RS. RE by RS. So we can find GB dash as well as we can find GD dash. According to this equation, we will get GD dash also. So we here GB dash and GD dash are equal and opposite. So as seen here, the value of GB dash and GD dash are equal but opposite in sign. So this inward, it is towards the center of the earth. And some important points regarding the tides or the conclusion. As a conclusion, we can tell that the apparent intensity of gravitational field varies from point to point. It is not same in all over the surface of earth. And this diagram shows various points on earth's surface, and we can start this field at different points are shown this figure, and analyzing this diagram we can easily explain the tides. The forces at A and C tend to lift the ocean. You can see it is tending to lift the oceans, while the forces at B and D tends to depress them. So if suppose this earth was uniformly covered with water, the tangential force components would cause the two tidal bulges in here, and like here and here. There will be two water bulges will be two tidal bulges to sweep around the globe with the sun will be there. So this diagram also tells us how these two tidal effects in a day happens. After 12 hours, the point C becomes in the position of B and B becomes in the position of C. This is that's why the two tidal effects happens in a day. This is the first example. So this is why the tidal effect occurs, and this apparent field is different at different points. We have considered 4 points, and it all having different apparent fields. And here next example 2, it is equilibrium height of the tide. We are going to calculate the height of the tide due to the sun based on a model divided by Newton. And for the solution of this, we are assuming that two wells full of water runs from the surface of earth to the center, where they join. Here it is joining. One is along the earth sun axis and the earth sun axis, and the other one is perpendicular. For equilibrium, the pressure at the bottom of the wells A and B must be equal. These are the two assumptions. After these two assumptions, we are going to the derivation, and for the derivation we are considering a small column of water of height dr as here dr, a small water column we are taking into assumption. Considering this small column of water of height dr, gravitational field is g of r, then the pressure due to this water column is given by dp is equal to rho into g of r dr, and rho is density of water, and therefore the total pressure at A is given by integral 0 to h1 rho g1 r dr. Similarly, the pressure at B is equal to integral 0 to h2 rho g2 of r dr. A condition for equilibrium is pressure at A is equal to pressure at B, that we have given at the beginning. We have assumed like that. Therefore, integral 0 to h1 rho g1 of r dr is equal to integral 0 to h2 rho g2 r dr. This is equation 1. And another assumption is that the water column is incompressible, so that rho is a constant. So we are taking away that rho because it's constant. There is in integration 0 to h1 g1 of r dr is equal to, we have omitted the rho since it is a constant. This is equation 2. And now our aim is to calculate the difference of or the height column height of the tide, that is h1 minus h2 delta hs. the height of the tide due to the sun, and hs means height due to the sun. This is, we are going to assume the earth is a spherical one and neglecting the effect due to its rotation, uh, and the effective field towards the center of the earth along column 1, and it is g1 of r is equal to g of r minus g1 dash of r. This is equation 3, where g of r is the gravitational field of earth and capital G1 of r is the effective field of the sun along column 1. In the last example, example 1, we have evaluated G1 dash of RE, R is the radius of Earth, it is as GA dash, and we have calculated it as 2G ms into RE by RS whole cube, RS cube. This, in this equation 4, we are substituting R, small r for RE, and we will get G1 dash is equal to 2G MSR by RS cube, or 2CR. We are putting capital C as the value, substituting GMS by RS cube. So equation 3, or equation 3 becomes, now we have got the G1 dash R, G1 G1 of R is equal to G of R minus 2CR, and G2 of R is equal to G of R plus G2 dash R. So G2 dash R we are substituting with G of R plus CR. We have already calculated it as 2C. The condition for equilibrium is integral 0 to h1 G of R minus 2CR into dr is equal to integral 0 to h2 G of R plus CR into dr. That is G2R, here it is G1R, this is G2 of R. On rearranging, we can take this expanding and rearranging G of R dr minus this term comes here, so dr into dr is equal to 2, this goes here, 2CR dr plus integral 0 to h2 CR dr. So combining the integrals on the left hand side, these two, we can write it as h1 integral h1 to h2 G of R dr, and h1 and h2 are close to the earth's radius, therefore G of R can be taken as a constant, therefore G of R is equal to G of RE, radius of earth, is equal to G. G is nothing but the acceleration due to gravity at the earth's surface. So the integral on the left hand side, here the two terms, these two terms we can take into account, and we can write this integral on the left hand side as G into h1 minus h2, h1 into G into h1 minus h2 is equal to G into delta hs. It is, hs means height of the tidal due to the sun. The integral on the right hand side can be written as due to h1 is approximated to h2 is approximated to radius of earth, therefore this integral 0 to RE can be written as, instead of 0 to h1 or h2, this 3CR dr is equal to 3 by 2 CR CRE all cube, so CRE cube. So final result, we can equate these two, G of delta hs is equal to 3 by 2 CRE cube. So we can, by using G is equal to GME by RE square, and we have C is equal to, we have already find C, what is C here, the value of C is GMS by RS cube, GMS by RS cube. So we are putting C is equal to GMS by RS cube, and G in the value GME by RE square. Delta HS is equal to delta HS is equal to 3 by 2. Instead of C we are putting this, so this equation becomes delta HS is equal to 3 by 2 into MS by ME into RE by RS whole cube into RE. From the numerical values like mass of sun, mass of earth, its mass of sun is 1.99 into 10 raised to 33 gram, and mass of earth is 5.98 into 10 raised to 27 gram, and the RS 1.49 into 10 raised to 13 centimeter. Radius of earth is 6.37 into 10 raised to 8 centimeter. Putting these values into this equation, we will get delta HS as 24.0 centimeter. This is the height of the tide due to sun's attraction, and definitely this height of the tide is there is similar equation for a similar argument for this moon also. Due to the moon there is some tidal effect is there. For that we will get the equation as delta HM is equal to 3 by 2 mm E by ME into RE by RM whole cube into RE. There is no difference between these two equations, but the substitution, we have to substitute the mass of sun by mass of mm, and RM is replaced to the RS. That the two changes are there, otherwise all are similar to the equation of delta HS, and delta HM is similar to except these numerical values. We have to put this moon's mass, and RM we have to put in this equation. We will get delta HM, the height of the tide due to the moon's attraction, will be 53.5 centimeter. So the delta HS is 24 centimeter. This delta HM is 53.5 centimeter. That means moon's effect is about twice large as sun's. But the sun's gravitation field is about 200 times stronger than the moon's. Then why this moon's effect is twice larger than sun's? There is a question like this. The answer is tidal force depends on the gradient of the gravitation field. The moon is so close that its field varies considerably across the earth, whereas the field of the distant sun is more nearly constant. So this moon is so close, therefore the field varies due to this closeness, and earth but the sun is more distant, therefore there's more, we are considering it as more constant, nearly constant value, and we got this delta HS and delta HM. And this is the example 2 to find the equilibrium height of the tide that we have now found out. Next our point is to find out the two ratio between delta H spring and delta H neap. These two terms may be new, but I will explain these two for you. This before that we all know that during the new moons and the full moon, the sun, moon and the earth are nearly aligned so the two tidal forces add to each other. During the new moons and full moons, the sun, moon and the earth are nearly aligned in a line, so the two tidal forces add to each other. During the quarters, sun and the moon are at right angles with respect to, so that earth and as a result produce an opposite tidal effect. With during the quarters, the sun and the moon are at right angles with respect to earth, and as a result it produces opposite tidal effect. So the strongest tides are called spring tides. These occur at the new and full moon. When the moon and sun act together, it will happen strongest tides. midway between the quarters, the moon, quarters of the moon, this occurs weak neap tides. So there are strongest tides called spring tides, and this is happening in the time of new moon and full moon. But in the midway, there are quarters of the moon that occurs weak neap tides. The ratio of the driving forces in these two cases is as given in this equation: delta H spring. The delta H spring, the strongest tides, they are called spring tides. So this delta H spring by delta H neap is equal to delta HM plus delta HS by delta HM minus delta HS is approximately equal to 3. That is we are getting. So if we are delta HM, if we want, that is like here, this delta H, delta H spring by delta H neap is equal to delta H M plus delta H of S. Delta H of M means tidal height due to moon, tidal height due to S, is tidal height due to sun, and delta H M minus delta H of S. The value will be, we know that due to the moon it is 53.5 and due to the sun it is 24 by 53.5 minus 24. It is getting approximately, the value will be 2.63. that we are approximately 3 in your text, though this is what we are getting, the ratio of the driving forces between the two cases of delta H spring and delta H neap. So let's wind up for time now. For this time, this maybe enough, and I'll come with some questions. If you have any doubts, contact me anytime. Thank you.